Last time we looked at the difference between homomorphic encryption and multi-party computation. This time what we're going to do is we're going to look at some use cases. They're not kind of really industrial use cases, but these are kind of use cases that have been investigated in various research projects at Leuven and in other universities. So let's start with our first use case. A very early one we looked at in relation to an EU project was looking at privacy in the smart grid. So in the smart grid, what you have is that you have homes record how much energy they're producing, and this goes to the energy provider, and the energy provider wants to use this information to predict in the future what energy consumption is going to be in the home. So obviously there's a security issue if you just reveal online what your energy consumption is, because obviously someone in the energy grid could then work out when you've left the house, what are you doing, etc. So this is kind of, there's obviously a privacy issue here, and obviously a security issue, because if people know when you've left the house, they can break into your house and steal stuff. So how do we actually get this data from the home to the energy provider in a way which allows us to predict energy consumption but nothing else? So the idea we had, which was kind of looked at by our industrial partners, was a privacy-friendly energy forecasting. Now obviously when you want to do some form of forecasting, you're going to use some form of machine learning. This project was done about 5, 6, 7 years ago. So in those days, computer encrypted wasn't as fast as it is today. And what we found was that there's a particularly a special form of neural network which comes from the 1970s, which was the first kind of deep neural network, but doesn't use the kind of activation functions that you see in modern neural networks. In particular, the neural network is really weird in that each neuron here, internal node, only takes input from 2 other previous layers. So you see this one here takes an input from this layer and this layer. And what it does, it then combines these 2 inputs via a polynomial of degree 2. So what we actually have is that the neurons are kind of produce this kind of very much, they all execute a quadratic function on 2 variables. Given that's an arithmetic circuit, you could easily do this within the homomorphic domain, because it's just evaluating homomorphic things. So the kind of data flow that you would have is that the energy consumers in their apartment blocks consume stuff. You kind of create an aggregate energy consumption for the whole block, because that kind of hides individuals. It's kind of like you can even add a bit of noise on to get some sort of differential privacy, so you get some aggregated information. And we can now pass this to an external untrusted company, which can look at the previous 47 consumptions, the temperature, the month and the current day, and predict a new consumption and get an encrypted forecast out, which then goes to someone else to decrypt. And surprisingly, this is actually relatively accurate. So we actually get a really good way of predicting in a privacy preserving way. However, if we're using homomorphic encryption, we remember back to our entities that we had last time, the green people, the blue people and the red people, the encrypted forecast has to go to someone else. So you actually have to have within the energy system a third party that is actually going to process the encrypted value. And it turns out that this, in many energy markets in Europe, this doesn't exist. So it's a theoretical exercise of how you would do this. But you see that mapping the FHE onto this, you have to change things. You have to say, we're not actually going to use a modern neural network, we're going to use an old neural network. We're going to change the machine learning to the specific problem. And we're also going to change, we actually have to have a specific set of parties. We have to have that the person who is actually doing this calculation, who has the possession of the neural network, is different from the person who's actually going to get the encrypted forecast out. And so that's a constraint on the market players, is who is actually operating in this market. So it's not applicable to everything. So you seem to have a secure computation problem, but you have 2 changes that you have to make to the environment to actually make this applicable in the secure computation manner. So it's kind of a nice story on why you just can't apply secure computation out of the box. Another one that everyone does is what's called genome-wide association study. Now, okay, what we're going to do here is we're going to look at this from the point of view of FHE and MPC and compare the two approaches and actually say that they're really not that much different when you look at them from a very, very high level point of view. So we've got a DNA sequence and we've got people with a disease and people without a disease, and we want to know if there's a relationship between the people with the disease and their genomes and the people without their disease and their genomes. So that's the kind of thing we're doing at the moment. So here we have 3 hospitals, say, and they want to do this operation on their patients without revealing their patient information to each other. So imagine we have 2 servers. We have a server that's held by the hospitals and some third-party server. Okay. So step 1 is that we're going to the decryptor. That's the thing on the left, the party on the left over here, is going to generate fully homomorphic encryption keys and then send the public keys to the various hospitals here. Step 2 is the hospitals are going to encrypt what's called their contingency tables, the link between the genome and the parties, and they're going to encrypt their data over to the compute server. Okay? Now the compute server is going to do the significance computation, which is just simply a chi-squared test. This is not a very complicated thing, it's just a bit of operation, not very much. And then the encrypted result goes back to the decryption server, and they decrypt and get the evaluation. Now notice what we've got here, that because of FHE we have a difference between the person who encrypts and the person who does the computation. We already have what's in some sense a multi-party computation anyway. We already have 2 servers. So what you could do, this is how you do it in a homomorphic encryption variant, but you could do it in an MPC variant where what happens is you have those servers. There could be 2, there could be 3. Here we've got a picture of 3, but it doesn't have to be 3, it could be 2, it could be 5, it could be 7, whatever. And here the hospitals secret share their contingency tables over to this MPC server, and the MPC server performs the computations on the secret shared data in a way that not all of them, they can't determine the actual values they're computing on, and then they reveal the answer. Okay, so we see that there isn't much difference between the FHE variant and the MPC variant, except in the sense of we still need 2 servers or more, but the MPC variant is much, much faster because it can compute stuff quicker. On the other hand, we do have to have a lot more communication. So you can see if you have this scenario, it's not clear which one you should use, FHE or MPC, depends on your constraints, depends on the entities, but you still have to have these entities in the system that are going to do. Is this going to work in the real world? Maybe not. The hospitals aren't really that well known for having really good IT systems and that can use very, very advanced new cryptographic systems, so they're going to have to outsource this to a third party who's going to be providing the third party, and you get into questions of business. Does this make sense? But the basic problem of doing computations on these genomes is in some sense a solved problem for this type of statistical analysis. So another one we looked at is image analysis. So this is kind of like we can do an image analysis thing. So you basically have the idea is, you take a picture and can you categorize the picture in sense of a bunch of possibilities of what it could be. And what you want to do is you might want to keep the picture secret, but you might also want to keep what you're testing for secret. It might be some, the model that you're going to apply, that could be commercially sensitive information. So here what we have is what we call EPIC, Efficient Private Image Classification. So, and this is an interesting one where how you kind of skin the cat in a completely different way. So here we have an image holder who's got an image. We have an image classification provider who's going to say this image is an image of, say, a dog, a cat, a house, whatever, or something more interesting. And then we have the person who gets the answer. Now, why do we keep these as 3 separate parties? Well, because the image holder, he wants to keep their image private, and the classification algorithm provider wants to keep the classification algorithm private. But the analyst, if the analyst was the image holder, then in some sense the analyst could actually keep querying the the secure computation and learn what the classification algorithm was, or learn an equivalent classification algorithm. Okay, so in some sense, if you don't keep the analyst separate from the image holder, then there's an obvious attack on the system. The system is, for if you allowed large numbers of queries, is by definition insecure from the point of view of the secrecy of the classification algorithm provider. And likewise, you can kind of say if the analyst was the classification algorithm provider, in some sense they're learning information about the image holder. So you could decide, I want to classify it, find out whether this image is of a man, a woman, or something. And so the questions you could ask would extract the information. Might not be able to extract the image, but it would extract the information that maybe the image holder didn't want to reveal. So there's a kind of, it makes sense to have three parties. And the next problem is, so that's like a structural architectural problem of the use case. The next problem is that image classification is really hard and it involves deep neural networks, usually to get the good results. However, what happens is that you can apply the deep neural network in the clear to the image, because you could take the off-the-shelf neural network and then you do this thing what's called transfer learning. You transfer a learning from one problem to another. So we want to do a classification of whether the image is a dog or a cat. But we could take, for example, the feature extraction neural network that's used, for example, for Google images, to do their Google Drive cars and stuff like that. So we could use that public neural network, which extracts features. And this features is a smaller amount of data. So this collapsing of the data can be done with the deep neural network, the really heavy lifting of the machine learning. And only that is put into the secure gateway in the MPC system to actually do the classification. So if you can kind of think of in old-fashioned days, this feature extraction could be, okay, the top of the image is all blue, the bottom of the image is all yellow. It looks like a beach scene because you have yellow and then blue, yeah. But we can do much more complex feature extraction by using a modern neural network to do the feature extraction, which can be applied in the clear. So we implemented this and we compared it to what was the state-of-the-art system at the time. This work was published in 2019 at CTRSA. The state-of-the-art system at the time was something called Gazelle, which appeared in Usenix. And for our version versus Gazelle, we're faster and we're more accurate. So if we just cared about, just the basic on what's CIFAR 10, which is a standard methodology for classification, we could have 34 faster times runtime with 50 times improvement in communication costs and be more accurate. And if we just wanted to focus on the same accuracy, we could be 700 times faster with a 500 times improvement in communication costs. So just basically just doing standard MPC and making the problem, moving the problem. Really, the key point is moving this problem, this feature extraction, out of the secure computation. We could be more accurate and get better classification. So it's kind of, you have to kind of change the way you think about these problems. So that was image classification. Now you can't talk about secure computation without talking about auctions. The classic example here is a very, it's from the mid-2010s, and it was to do with the sugar beet auction in Denmark. It's run by a company called Partisia, and they're still in operation doing auctions. Now, an auction is very simple, really. What we have is that we basically have what we want to get out of an auction is you want to find a clearing price for a certain amount of items, of stuff. And that's what an auction does. And you can do this in various ways. But basically, economically, what you're trying to do is work out the clearing price. And the clearing price is the point where the supply and the demand curves meet. So if you're trying to sell some stuff, the sellers, if the price is low, are not going to want to sell too much. So if the price is 1, they're not going to want to sell too much. But if the price goes up, the sellers want to sell more. There's more incentive for them to sell. On the other hand, from the point of view of the buyer, the higher the price, the least amount of stuff they want to buy. So the clearing price is when we maximize the utility for the buyers and the sellers, which is where these two curves intersect. So that's essentially what an auction's trying to do. I mean, there's different ways of doing this. We use contingent double auction. There's loads of mechanisms to actually do this, but from a very, very high point of view, this is what we're trying to do. So one way you could do this is actually get the buyers and the sellers in a market to enter what their personal supply curve is or what their personal demand curve is. You can then work out the aggregate supply and demand curves by summing them, and then to work out the clearing price, it's just simply a binary search, because we could subtract the supply curve from the demand curve and then work out where that final curve crosses the x-axis, and we can see where it goes positive or negative, and to do that we can use binary search. So that's essentially what Partisia did in the mid-2000s. It's a very old way of doing it. So could we kind of revisit this? So in recent work we've been looking at dark markets. So dark markets are like a dark stock market, and in the sense that you don't, when you want to buy and sell large amounts of stock, if you sell a large amount of stock you affect the price. If you buy a large amount of stock you affect the price. So the fact that you intend to buy something is actually something that can affect the price, and that can be detrimental to you. You're about to buy a lot of stock of company X. Everybody else notices this, so they buy, and then the price goes up before your big order can go in, before you find a seller that wants to match your buy order. So dark markets exist to kind of keep this information off the clear market, the so-called lit market, so the price swings can be mitigated. So you can put an order in, and your order doesn't actually affect the market until the price in the market, until the order is actually met. In normal dark markets, the dark market operator acts as a godlike figure, but they can cheat. They can do what's called front running. They can see the bids coming in because they're the god, and then they can delay, or they can utilize the gap between the big bid coming in and the big bid being met to actually put their own orders in and profit. And that's one, illegal, and two, it's not really playing fair because it's illegal. Yeah, kind of obvious. So what we did in a recent Asia CCS paper is we looked at how we could look at dark markets and try to execute dark markets in a kind of real-time manner. We looked at the very different mechanisms and see how they could be transferred to the MPC arena, because if we can execute the dark market in an MPC fashion, then the dark market operator does not actually see the incoming bids again until they're met. So we can remove this problem of front running. So that's something we've been kind of looking at recently. And using the system that we developed in Leuven, we're able to process a reasonable number of calculations later on. If you follow the course, later lectures, you'll see what we mean by the speed protocol. You'll see what we mean by Shamir 1 out of 3 sharing. But we can process, if we did what's called a volume matching order, we can process thousands of orders per second. Or if we did the kind of traditional, what's called a continuous double auction method, we can process hundreds of orders per second. So given that these are very large trades, so they're not the kind of high frequency trading of the other side of the stock market where you're trading things very, very quickly. These are for really, really big orders at the end of the month when a pension fund is rebalancing its stock portfolio, for example. In future work, we actually looked at extending this, how it extends to, we could extend it to other forms of dark market operations, so not just the single double auction, but volume matching. And this is kind of an interesting application, because it doesn't just apply to dark markets, it can apply to all sorts of operations where you want to do an auction, which occurs in a number of situations in industry, when you're trying to allocate resources. A classic example of using MPC is to do analysis of two databases. You want to combine two customer databases, say from two different bank accounts, but you don't want to, for privacy reasons, want to share that data. For example, you might want to produce, using MPC, a combined credit score, so you can combine the credit score with one bank with the credit score of the other bank, credit scoring mechanism, combine them to get a better credit scoring mechanism, but without revealing each bank's customer data to each other. And this occurs all over the shop. So there's been a really classic example of this is the City of Boston did a gender equality survey where they got data of the amount of money paid to men and women across various companies, combine them and produce statistical data which summarise that. There's been a classic example of Estonian tax and education analysis done by the company Cybernetica. There's been a US government move for more student outcomes, what's called Know Before You Go, which we'll look at in a bit. And this is kind of part of what Senator Wyden and others in the US Congress have been looking for, to creating a form of evidence-based policy making. And most of these things are about producing descriptive statistics. They're about doing averages. They're doing standard deviations, histograms, just describing very basic statistical information. And this is all kind of doable with secure computation for a relatively large amount of data. So we were kind of looking at this in a DARPA funded program called Brandeis, where we're working with Galois, who produced the JANA database, and they were using our system to provide the MPC backend to their database. And we were looking at applications in US Census, potential UN applications. But combine this also with differential privacy, because when you do a secure computation, remember we go back to the very beginning, you reveal everything about the underlying data that's revealed by the answer. So the answer itself could reveal private information. So to avoid that, you need to add, not only do secure computation, you also need to add differential privacy to stop that happening. So what's JANA? Well, it combines our system with a query rewriter from Galois. So dynamically, the SQL queries for the database are dynamically written into scale bytecodes and executed on the MPC engine. We looked at a number of applications in US government in this, mainly about knowledge-based policy. So, for example, we could look at Know Before You Go. We've already mentioned Senator Wyden pushing this in a number of applications in the US. So here you have this kind of idea that the Know Before You Go Act was a way of trying to get data to students before they go to university about information about the course outcomes. Now here you want to combine various information. You want to combine the census information, you are from a given background, a given area of the country, given amount of deprivation or benefits of being in that area. You want to know what happened when people left university, whether they got really good jobs, whether they got good employment, and from that that data, you don't actually have to talk to all the companies for that. You can actually just get that from the IRS. You can get how much tax did they pay as a pretty good correlation of how much they earned. You can look at how much their loans and grants were when they went through university. You look at institutional information from the universities, whether they gave the student a scholarship, what their degree program was, what dates they went on, and maybe if you're coming from ex-army. Maybe there's a GI service record that when you leave the army you get a chance to go to university. Maybe there's some information there. We can do that analytics on that integrated data and then provide information to the prospective student on the expected time, the expected cost, the graduation rate, etc. But notice we're actually pooling 5 or more sources of information here, and there's no way the university wants to give all of its information over to the IRS. The IRS doesn't want to give its information over to someone else, the Census Bureau. So all these are private information, but we want to obtain the utility of combining these information together to produce relatively simple statistics at the end. And this is a classic example of where we can use secure computation. So finally, I want to talk about an application that's close to my heart, which is securing cryptographic keys. So here we're going to do the opposite of combining data together. In the previous thing, we were taking 3 databases, 5 databases, 10 databases, combining them into getting utility out of combining them. What we're going to do here is actually take data and split it apart and actually gain more security by splitting data up. So we use cryptographic keys everywhere. We use them for password authentication, code signing, all sorts of stuff. A classic way of securing cryptographic keys is to put them in what's called hardware security modules. These are like specialized computers which only allow you to do cryptographic operations, and they control access to the key. And HSMs go through a validation process to show they meet certain minimum security requirements. Now, but the problem with HSMs is they're not very flexible. They kind of don't really meet the kind of concept we have these days of elastic compute capability on the cloud. So they're a bit clunky. So so they've got problems. They're expensive. One of these boxes could cost you $10,000, $20,000. they're not that secure. They have kind of various API issues. Updating them is complex because they're hardware modules. You often have a lowest common denominator security. If you're trying, HSM1 is talking to HSM2, then in some sense you have to kind of talk the language that the oldest one talks. So for example, one HSM might talk CBC mode with only the 0IV key, which is not secure, and then the other one might be able to support GCM mode with arbitrary IVs. But the new one has to talk, if it has to send something encrypted, the other one has to talk in the lowest possible cryptographic denominator, so that just kind of might be an insecurity. You need a huge footprint with these things because they're non-elastic, they're hardware modules, so you need as many of them as your maximum load during the day. They're a very inflexible API, and they're not integrated with the authorization infrastructure, which is a big issue for things like code signing or cryptocurrency. So myself and Jutta Lindell had this idea of taking the cryptographic key and splitting it up. So instead of holding the key in the HSM, what we do is we take the key and we split it up and we hold it in different locations. And then we can do the cryptographic operation, not by bringing the key ever back together, but doing the cryptographic operation via MPC. So this is the company we formed, Unbound Tech. So what we kind of do is produce, in some sense, an HSM which uses MPC to do this right thing. It was the first MPC system to get US validated FIPS level 2 thing. Been major installs in financial in institutions, and code signing by a major computer company. So it's also got applications in cryptocurrency. So that's kind of another application where you take data and you split it apart. So having looked at all those use cases, you can see that there's more interest, there's more places you can apply secure computation. I mean, this is just a Gartner hype cycle from 2018, one of the Gartner hype cycles from 2018, which mentions MPC. So you can see this is getting more traction in industry, and analysts are now knowing that this is a kind of technology that can be applied. And there's various hype cycles mentioned in MPC and FHE, etc., etc. And there's a bunch of companies in this space. There's loads of them. There's lots of we've already talked about Partisia, Unbound, and ShareMine, but there are others in the space. In the FHE space, we've got Enveil, Duality, Zama doing FHE style stuff. We've got other people looking at MPC, CPUR, Zengo. We've got organizations like Privitaro looking at things like to do with federated learning. We've got Intel looking at FHE investments. There's all sorts of people using MPC, FHE, and other forms of secure computation to do interesting applications of doing computation on encrypted data. So I hope you found some of those use cases interesting and kind of motivating ideas and some of the issues you have to worry about as we go forward. And in future, what we're going to do is go into deep dive into the tech to understand what's going on. So thank you for listening.